Alright guys, welcome back to day 2 of our functional group extravaganza, I guess you could call it. So yesterday we covered a little bit about the alcohols and ethers, kind of in our oxygen family. And today we're going to move into the green, kind of carbonyl compounds, and we're going to talk about aldehydes and ketones. So let's go ahead and get started. And the learning targets kind of for this section are very similar to what we did yesterday. We'll start out just by recognizing those functional groups, naming and drawing them, predicting some products, and then you'll kind of end off with looking at some real life applications. Okay, so basic structure. What both of these things have in common is what's called a carbonyl. And what that looks like is you have a carbon that's double bonded to an oxygen. And so that's something that the ketone and aldehyde will share. What is different is that aldehyde, the carbon is going to be connected to a hydrogen on one side and the remainder of a molecule on the other side, while the ketone, instead of being connected to a hydrogen, will just be connected to another part of the molecule. So either some type of CH group or a ring, just anything kind of like that. And so it's kind of like an ether, how the molecule continued on either side. So that's the catch there, is the H on the aldehyde. Okay, and that's what sets them apart. Now, let's go ahead and take a look at some electron density kind of planning out. So we know that the difference is going to be occurring here with this oxygen and carbon. Oxygen is more electronegative, so it'll have a partial negative charge. This carbon, on the other hand, is less electronegative, so it'll have a partial positive charge. And this is a typical characteristic of a carbonyl compound, where you have the carbon with a partial positive charge and the oxygen with a partial negative charge. And so this is going to make that carbonyl site a great place for reactions to occur. And so typically the pattern that we see is some sort of nucleophile, something with extra electrons to share, is going to come in and interact with that positive, partially positive carbon, and then the reaction will proceed from there. So it's something just to kind of be on the lookout for. All right, so now what let's practice is let's see if we can locate some aldehydes and ketones in retinol and acetyl-CoA. And I'll tell you what, since we got a feel for how this works yesterday, go ahead and pause the video and see if you can do both of those, and then unpause and we'll kind of walk through it together. All right, so this first compound here is retinol, as you might guess. Kind of reminds you of retina, which has to do with our eyes. And so what I found for this one, if we're doing our aldehydes, is I found an aldehyde on the end where you have that carbonyl group attached to a hydrogen. And I actually didn't see any other carbonyl compounds, so no ketones there. All right, so now let's see if we can take a look and find some ketones in this other section. So I found one here, and what makes this a ketone instead of an aldehyde is since there's just a point here, that means that this is a CH3 group. So that's like kind of an R, the rest of the molecule. We've got kind of a ketone here, which later on we'll find that has a different name, or we may not get to that. But anyways, it kind of looks like a ketone for our purposes now. Have one there. Let's see, and I think that's it. All right. So now that we have talked about recognizing them, let's practice a little bit of overview on the naming side. So aldehydes, when they are the main functional group, the ending or the suffix is going to change to al, all right? If, however, they're attached to a ring, you'll use the full ending of aldehyde. And so kind of some examples here. So you have ethanol. The reason it is eth is because you have 2 carbons, 1, 2. You have propanol with 3 carbons, butanol with, you guessed it, 4 carbons. So it's using those same kind of prefixes, meth, eth, pro, bu, that we've encountered before. And then this last one, you have benzaldehyde, which this is when it's attached to a ring, and so we're using the full ending of aldehyde. This is a benzene ring, so that's where the benz comes into play. Now what you'll notice is unique about aldehydes is in none of these examples did we have to say 1 propanal or 2 butanal. We never had to number to show where the aldehyde was. And the reason for that is that the aldehyde always has to come at the end of a chain in order to leave enough room for it to have that hydrogen there, okay? And so if it always comes at the end of the chain, we're just going to assume that that is the starting point. We'll start from whatever end of the chain that is. And so that means that the aldehyde will always be on the first carbon. And so there's no need for us to number it in that case. So now if we go over and look at the ketones, when the ketones are the main functional group, the ending, the suffix, will change to -one, O-N-E. Okay, and so we've got some examples here. We've got 2-propanone, which is actually the structure of acetone. And the reason it's prop, again, is since there are 3 carbons there. Now, what you will notice about the ketones is that they do need a number, when you can have them on more than one possible carbon location. And that's, again, because a ketone typically has to be kind of within a molecule in order to kind of satisfy that need to have some sort of chain or group on either side. So you've got 2-propanone. We have 2-butanone, but for the 4 carbons. 3-hexanone, that's on the 3rd carbon, and our chain overall has 6 carbons. That's where the hex comes in. And then we also have kind of another group where we've got our ketone here, and it's attached to a benzene ring. In this case, the benzene is treated as a substituent, and it's called a phenyl group. And what you'll notice that sometimes happens is just like we did for the ethers, where we named kind of one side and then the other side. That's what's kind of happened here as well, where they've named the phenyl group on the left, then the methyl group on the right, and they've just used the name ketone. So phenyl, methyl, ketone, that just means you have a phenyl on one side, a methyl on the other side. And they gave us an example of that here as well on the second one, where you could have named it methyl on the left, ethyl on the right, and then the ketone in the middle. So those are just a little more common names. The 2-butanone would be. Alright, so let's try out this naming and drawing here. So our first compound that we have in question is an aldehyde. It has the carbonyl compound attached to that hydrogen at the end there. And so we know we're going to use the ending of al. And so let's count to see how many carbons long our chain is. So we've got 1 carbon, 2, 3, 4, 5 carbons there. So this is going to be a pentanal, if you will. 1, 2, 3, 4, 5. So this is pentanal. And again, we don't have to tell which carbon the aldehyde is located on, since it will always be the first. But we do have a methyl group that's hanging out on the second carbon there. So this will be 2-methyl pentanal. All right. Okay, so now let's go on to this next one here. In this next case, we've got a ketone. It's got more carbon groups kind of on either side. And so let's go ahead and count our carbon chain to see how long it'll be. So we've got 1, 2, 3, 4, 5. So the ketone is on the 3rd carbon, and out of 5, so our ending will be pentanone, and the ketone is on the 3rd carbon. But then we also have a methyl group on the 2nd and on the 4th carbon. So we'll call that 2,4-dimethyl 3-pentanone. All right. Now, this one is a little bit different. It's a ketone, again, because you have the rest of the molecule continuing on both sides of the carbonyl. But this one happens to be a ring compound, so we'll be using the prefix cyclo. So let's go ahead and count here and see how many carbons we have. 1, 2, 3, 4, 5, 6. All right, so this will be a cyclohexanone. And again, if it's a ring compound, if it's a ring compound with one ketone, the ketone will be the first carbon, and so there's no need to provide a number in this case. So just cyclohexanone. All right, now last one, it gives us a ketone and an aldehyde to try to draw here. So the first one, let's kind of start with the base first. So it's a heptanone with the ketone on carbon 2. Well, so we'll go ahead and draw a chain with 7 carbons. 1, 2, 3, 4, 5, 6, 7. And we'll put our ketone on carbon 2. I'll just choose it to be the second one from the right here. We could have put it on the left as well. Either way would have worked. All right, and then it says on carbon 4, we need to put an ethyl group. So this is 1, 2, 3, 4. So an ethyl group would have 2 carbons. So 1, 2. And then on carbon 5, we need a bromo group. So that will be our bromine there. All right, now let's look at the next one. This is a heptanal, so that means instead of a ketone at the end, we're going to have 7 carbons but an aldehyde. So 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. So that's 7 carbons. And again, the aldehyde always goes on the ending carbon. And you have a hydrogen there at the end. And sometimes when aldehydes are drawn, you'll see them just leave it kind of as a double bond. Because remember, you would assume that you have enough hydrogens to complete the octet. So you can either leave it like that or go ahead and finish it off by adding a hydrogen. All right, so then on the third carbon, we need an iodo, which is iodine. So we've got 1, 2, 3 carbons. So here's our iodine. Then on the 5th carbon, we need bromine. So it's 1, 2, 3, 4, 5. So there's our bromine. So 2 halogens attached there. All right, so nice work. So, doing our kind of brief intro to naming and drawing. And so what we're going to take a look at for our reactions is kind of some addition reactions to aldehydes and ketones. And so typically these addition reactions will kind of occur in a 2-step pattern. One, you're going to have the attack of the nucleophile. And then you'll be doing a step that's called protonation, and that has to do with a proton H+. And like it says, an aldehyde is shown here in the general example, but also applies to ketones. And so the general pattern that you're going to see is that you're going to be breaking one of these pi bonds between the carbon and oxygen. So there'll no longer be a double bond there, and you're going to be forming 2 new bonds. The first new bond will be between the nucleophile and the center carbon. Then the second new bond that we'll have will be between the oxygen and an incoming hydrogen from this protonation step. So let's take a look and kind of see how this normally takes place. So this is just in general kind of the 2-step mechanism that occurs. So again, because this carbonyl has kind of a partially positive carbon at the center, that makes it a great site for a negatively charged nucleophile to come in and attack. So we see the nucleophile attacking at that carbonyl base, and so those pi electrons, one pair of those get transferred up to the oxygen. So at this point, the oxygen will have kind of 3 lone pairs, and the nucleophile is now attached to that center carbon. So here's the carbon that was originally at the base of the carbonyl. Now what we're going to do is, since this oxygen has a negative charge, we're going to protonate it by giving it a hydrogen. And so in essence, what we're going to be forming is an alcohol at the end of the day. And now that we know more about functional groups, not only can we start to say, oh, this bond was broken or this bond was formed, but we can also start to classify our products by saying, oh, we've also formed, by doing one of those bonds, an alcohol. And so what happens in the protonation step, this comes from adding kind of acid in the second step. Acid is typically represented as H3O+, which if you drew it out, kind of looks like this little dude right here. Or they're kind of showing it in this way, H2O with an extra hydrogen attached. But what happens is that places a positive charge on the oxygen. And so the resulting protonation step, what happens is this negative from the oxygen is going to come and claim that extra hydrogen from the hydronium kind of water molecule with the extra H. That allows these bonding electrons to be donated to that O and kind of satisfy its need to minimize the formal charge. All right. And so then that results in a new bond between the O and the H, which gives us an alcohol. Okay? And so essentially, we've inserted a new group in terms of the nucleophile, and we also have an alcohol attached to that same carbon as an end result. And so we're going to do, kind of for our practice, kind of one specific example of this type of addition reaction, which is called a Grignard reaction. You'll definitely hear about this in college if you take OChem, and I remember doing this in our labs a couple of different times. And so what's special about a Grignard reaction is the nucleophile that it allows you to add to that carbonyl carbon center. And so what it allows you to do is actually add pieces of an alkane. So that means CH, CH2, CH3 groups that are carbon and hydrogen containing. Now normally when we look at CH3 kind of by itself, it doesn't look like a very good nucleophile. Carbon and hydrogen have roughly the same electronegativities, so it doesn't really have any extra electrons that are good for attacking something else. And so what happens, and why it's called a Grignard reaction, is in the first step they use something called a Grignard reagent. Okay? And what you'll notice is the Grignard reagent has a metal as a part of its chemical structure, and that metal is attached to that alkyl CH3 group. Now metals are very good at donating their electrons, which is why they often take on a positive charge as ions. And so what this does is the fact that this CH3 is connected to a metal is it gives that CH3 seemingly more electron density, and so that's going to make it a better nucleophile. All right, and so that's what's really neat about your Grignard reagents is they turn just plain old CHs into nice nucleophiles. Okay, and so what we're going to do is kind of walk through this mechanism just one more time, kind of on a specific example here. And we are starting with an aldehyde in this case. And again, at the end of the day, what we should end up with is on that original carbon, we should still have our oxygen, but in this case, it's going to be bonded to a hydrogen from the acid. And we'll also have the nucleophile that's been added. And in this case, the nucleophile is going to be that CH3. Okay? All right. So we're going from an sp2 carbon to an sp3 carbon center there. Okie doke. So let's start and just kind of walk through the mechanism one more time. So here's our oxygen. All right. So the first step it said is we have the attack of the nucleophile. And again, due to the special structure of the Grignard reagent, the CH3 is going to act as the nucleophile to attack that partial positive carbonyl center. Okay? As a result, these pi electrons will be donated kind of up to the oxygen. So those are its starting electrons. So our first step was nucleophilic attack. Then now that oxygen will have its extra electrons, so it'll have a negative charge. And we now have the CH3 attached as well. The MgBr will just kind of be, it won't go into like the final product. It's just used to make the CH3 a nucleophile. Okay. So now the last step is to add some acid and go ahead and protonate that O. So we've got our acid here, our H3O plus. And so that negative charge, if we kind of draw it like they did in our example, so it's kind of like water with an extra hydrogen. So that negative charge can reach out for the H. That can be donated back to the water. And so our final kind of product at the end of this will be an alcohol. And we still have the CH3 group attached at the bottom. All right, and if we wanted to, we could even erase CH3 because technically just one line there means that it's a methyl substituent. So either way is just fine. But there's our Grignard reaction product. All right, so last two practice problems before we send you on your way. So it says fill in the boxes with the correct structures. On the first one, it asks us to predict the product, and on the second one, it asks us to predict the reactant. So we know in a Grignard addition, we've got kind of our Grignard reagent with the magnesium bromide, and then our second step is going to be acid. In this case, we're starting with a ketone. And this is making me realize that I forgot to copy the hydrogen in the previous problem. Sorry, Mr. Hydrogen, didn't mean to leave you out there. So it was an aldehyde in that case. So back to this one. So we're starting with a ketone. And so this carbon here is going to be the site of interaction. So the rest of the molecule will stay the same. So I'll go ahead and draw that part in there. And what we know will happen kind of at that point is we should result with an alcohol from the oxygen, and whatever the nucleophile is should also be attached. The nucleophile is kind of the carbon chain that's attached to the Grignard reagent. So in this case, it's going to be these kind of 3 carbons here, which are in an isopropyl sort of arrangement. So we're going to attach our 3 carbons, 1, 2, 3, and they'll be attached to that carbon now. So let me tidy that up there. All right, so there we go. Now, if we wanted to predict a reactant, we kind of need to backtrack and see what we've added to that carbon center. So here's our carbon center with the alcohol. So we know that must have been where the reaction initially started. So let's go ahead and draw in this ring because nothing will have changed here. That's not a part of our reactants. So we've got it's a 5-membered ring. It has a little methyl group on the side. And then here's our carbon of interest. Now we know this alcohol would have started as a double bond to an oxygen, so a carbonyl group, all right? And now what we need to look at is what has been added from the Grignard reagent. So this little cyclopropane group is what has been added on, all right? And notice we don't see any other groups on this main carbon. So that must mean that that 4th bond is a hydrogen, which tells us we would have started with an aldehyde. All right, so that kind of lets us figure out our reactant was an aldehyde. Okay. So good job. Again, just the main thing, we're throwing this out there to kind of expose you, hoping you'll kind of pick up some of it as you go along. But now I want to give you a chance to kind of see where some of this comes into play. And you're actually going to be looking at some of the scents of flowers in a little compound chemistry article. This is kind of the wrong picture there. I had 2 slides up at once. But what you'll be doing is when you get to the website, you will be clicking and kind of enlarging this graphic, and it's going to show you some different chemical structures that result in some different scents that we associate with different flowers, such as roses, carnations, kind of so on and so forth. And also it's got kind of a short little summary article underneath that you'll be reading. And then there's a little file on Google Classroom that you'll pull up, and it'll again give you the link to the article, tell you what to do while you're there, and it'll have a few questions for you to think about and answer to help you connect the real life application to what we learned today. All right, well guys, y'all